Welcome to Your Math Explained, where we make math simple and clear. My name is Julian, and today we'll look at two combinatorics problems that involve counting techniques. The first problem is for grade 9 and 10 students, and the second problem is for grade 11 and 12 students. In both problems, we rely on counting strategies, and we'll also use this opportunity to introduce you to some new notation. Pause the video now if you haven't had a chance to read it, otherwise, let's jump in. In this problem, we're looking for probability. And anytime I see that, the first thing that comes to mind is how to create that probability statement. We would like the number of favorable outcomes all over the total number of outcomes. So I'm going to start with the bottom. We would like to figure out the total number of outcomes, meaning how many different 4-digit tickets there could be. So we'll write that down over here. Total, I'll just say total. The ticket consists of 4 characters, and these digits can be repeated. So I could have a 0000, the next one would be 0001, and so on. In each character, I have 10 digits to choose from, the numbers 0 to 9. So I'll have 10 choices here, 10 choices here, 10 choices here, and 10 choices for the last character. In order to calculate how many tickets we have altogether, we simply multiply these 4 numbers together to make 10 to the power of 4, which is 10,000 possible tickets. You might wonder why we need to multiply these 4 numbers together. An easy example to consider would be to consider the situation where you have 2 shirts and 3 pairs of shorts. How many different outcomes or how many different possible outfits could you have? You simply multiply the 2 shirts by the 3 pairs of shorts and you'll get 6 different outfits. And that's the same thing that's going on here. We have 10 choices for the first one, 10 choices for your second character, and so on. So pretend like there are 4 different articles of clothing and you need to combo them up in all of the different ways. This actually has a name. If you want to look this up, this is also called the fundamental counting principle. Now we need to think about the numerator, the number of favorable outcomes. And we would like to figure out how many different tickets have a sum of 34 or higher. 34 is a pretty big number, of course. We would want to figure out what the maximum sum would be, and that, of course, is 36, because 9 plus 9 plus 9 plus 9 makes that value. So right away, I know that if we have 4 9s, I could have the possibility of 9999, and those would work. And there's only one way to make that happen, right? That's the ticket 9999. So then my next thought would be, okay, what happens if I have 3 9s? Well, I would have a 999, and what are the allowable outcomes for the last value? Well, if 3 9s exist, that's already a sum of 27. And that means I need at least another 7 to create 34. So I could definitely choose 7. Now, if I can choose 7, I can definitely choose 8. So I've got those 2 choices at the moment. I don't want to put the 9 there because that would just be the same scenario that I did up top. I already did 4 9s. So these would be the acceptable combinations. Now, I haven't considered all the permutations yet. So permutations is the number of orderings of these values. So right now, the way that I've written it, it looks like it's 9997 and 9998 as the 2 possibilities. But the 7 and 8 could be in any of these positions. It could have been 7999 or 9979. So I'll deal with the orderings or permutations in the next step. I just want to figure out how many different numbered combinations there are first. So we've tackled 4 9s, we've tackled 3 9s, we're going to tackle 2 9s next. If we have 2 9s, so let's just say we have 18 there, what are some of the other possibilities? Well, I don't want another 9 because then it would fall into the previous category. So let's try the next best number. If we have an 8 there, we now have 18 plus 8, which is 26. And then to create a sum of 34, I would need another 8. So this is good. I could have 9s there, but then it would fall into that 3-9 category. So this is the only way to create 34 with 2 9s. If we have 1 9, so let's try this. We'll have 1 9, and then let's say it's an 8, and let's just try to maximize this if we can. This would be 24 plus the 9, and that only makes up 33. So this is telling us that there is no way for us to create a sum of 34 or higher with 1 9. So we can eliminate this possibility. So now we need to expand on the number of tickets in each of these scenarios. With the 4 9s, we can already see that there's only one ticket, because that's the ticket with 9999 in it. When we have 3 9s, I think it's pretty easy to determine. So let's just assume that we're working with the 9997. Well, the 7 could be in a lot of different positions. It could be in the first one, second one, third one, or the fourth one. So there would have been 4 different orderings with the 7, and that means there are going to be 4 different orderings for the 8 as well. So we are going to have 8 tickets from this scenario. And again, if we're not following that logic, we can just list those out. We would have 9997, 9979, 9799, and 7999. And simply replacing those 7s with 8s will give you the other 4. In the context with 2 9s, this one's a little bit trickier because there are more combinations to count. It's still reasonable to count it out. Like, I can totally just start writing the combinations. 9988. We've got 9898. You see that I'm just bumping that second 9 further along the list. So now I would try 8998, 8989, and then 8899. And already we've come up with all the possibilities. There's 6 tickets here. But if we were wanting more complicated calculations, we wouldn't want to count it this way because it takes too long. So we might want to introduce you to a new notation called factorials. Factorials is a simplified form of multiplication. So if somebody wrote down 4 factorial, this also means 4 times 3 times 2 times 1. You multiply the positive integers down to 1. It is a pretty well-known formula where if we wanted to calculate the number of orderings of objects that have repeated objects, it is n factorial over n1 factorial, n2 factorial, up to n sub k factorial, where the n sub 1, the n sub 2, and the n sub k's, those are the number of repeated objects, and the n without the subscript is the total number of objects. So in this case, we can maybe write down the restriction right beside here. n1 plus n2 plus all the way up to n sub k sum up to n. So if we were to use the formula here, we can turn this into 4 factorial because we're trying to order 4 objects. And we have 2 9s and 2 8s. So those are the number of repeated objects. And if we were to simplify, that would be 4 times 3 times 2 times 1 on top, based on the factorial notation that we just saw. And on the bottom, I got 2 times 1 times 2 times 1. And we can see some cancellation. And that's going to leave us with 6 tickets. So this is another way that we can count the number of tickets with repeated objects. So that was a nice detour. Back to the original problem. We've got 6 tickets in this last scenario, 8 tickets in the second scenario, and 1 ticket in the first scenario. So that means we have 1 plus 8 plus 6. That's 15 tickets out of 10,000. So So 15 out of 10,000 is the probability. And if we wanted to reduce this, we can divide it by 5 and we'll get 3 over 2,000. In the second problem, we are going to utilize a similar strategy, and I'm going to use factorials to help us again. The fact that we're dealing with probability again means we should probably find the total number of 3-digit positive integers. So the total right away, well, I've got 3 characters to fill out. If a number starts with a 0, that's no good because then it's not a 3-digit positive integer. So I can't actually start with a 0, which means I have 9 different options to choose from, the numbers 1 to 9, and then I can choose from the 10 digits for the second character and the third character. So using the fundamental counting principle again, this is going to be 900 total possibilities. My next step is to try to figure out how many of those 900 will sum up to exactly 15. So in my mind, I'm going to start trying some values and just see what happens. So let's say I have 1 as my first digit, 9 as my second digit. So I pick the minimum and then the maximum, and then I just want to figure out what the remaining digit would have to be. That's going to be 10, and we need a 5 to create the sum of 15. So this is one set of numbers that can create the sum of 15. And again, I'm not going to count the orderings of this just yet. We'll try to move on this list. We'll have 1, 8, and that's going to give us 9. So I need 6 for my last one. And then I've got 1, 7, 7. And already we can see there's 3 lists of numbers. I could move on, but at this point, I'm already seeing something interesting. The number of orderings here, because there are 3 unique values, that's going to be a different calculation than the number of orderings here, because I've got some repeating 7s. This idea is giving me a strategy. Maybe I should start classifying the cases as repeating digits because they're going to fall in similar classes and they calculate in a similar manner. So I'm going to start making a list on the side where we are going to involve 3 different cases. The first case that we'll want to look at is 3 repeats. So if we have a 3-digit number that is repeating 3 times, what number would that have to be to make 15? And that one is pretty obvious. That's going to be 5, 5, and 5. There's no other way for you to get 3 repeating numbers to sum up to 15. So there's only one possibility in this scenario. Consider the scenario where we have 2 repeating numbers. Well, what could we have? We can certainly have 3 and 3. So that would make up 6. That means I need a 9 for my last digit. I could also have 4, 4, which means I'll have a 7. I can't do 5 because that would be 5, 5, 5, which I've already counted up top. So we'll move on to 6. 6, 6, that's 12, so we need a 3. And then also we've got 7, 7, and 1, as we just saw in the initial count. So we're going to be able to count the number of permutations here with the same repeated objects formula as earlier. Each one is going to be calculated as 3 factorial over 2 factorial times 1 factorial. This is the formula that we used above. And then this is the same as 3 times 2 times 1 over 2 times 1 times 1, meaning there are 3 orderings of each of these 4 categories. So we can do 3 times 4, and that'll give us 12 overall combinations. The last category will be no repeats, or just 1 unique character each time. So I've already started counting on the left side, and I think the best way to do this is probably just to continue the count. I got to this 177, So that's already counted in my double, so I'm just going to eliminate that now. If I continue with this pattern, you see the next one is going to be 168. But 168 is just a different ordering of 186. So I actually don't need to go any further. I'm just going to start getting repeats. What I should do is then move on to numbers that start with 2. So if I have a 2 and then I pick the maximum for the second character, I've got 11 now. Then my last one would have to be 4. And then I'd have 285. I'd have 276. And then the next one would be 267, which is just going to be a reordering of this one. So I don't need to go any further. I guess I can write that down. I'll cross it off just to signify that we don't have to continue on. Next, we've got 3, 9. So that's 12. That means it's a 3, but we don't need to worry about that because that was in our 2 repeat scenario. So then we move on to 3, 8, 4. That's okay. The next one would be 3, 7, 5. That's okay. These are all unique ones. But the next one would be 3, 6, 6, which has shown up in my 2 repeats. So I can get rid of that. If I do the next one of 3, 5, 7, it's a reordering of this one up here. So I don't need to go any further. With the 4s, I've got 4 and then 9. So that's 13 and 2. But that's a reordering of 294, so I don't need that one. We can continue until we see some doubling. So 483, we've got the 384 over here, so we don't need this one. 474 is a double, so we don't need this one. And then 465, we don't have that combination yet, so we're good. The next one's 456, so that would just get eliminated because it's a reordering of this one. And we can proceed in a systematic way. So we've got 5s next. So 5, 9, 1. So that's my 15. We already have a 195 up there, so we're good. 5, 8, 2. And we have the 285 up there. 5, 7. And then that would be 3. But we got a 375 already. So we're seeing that there's going to be a lot of cancellation already. So we got 5, 6, 4 as my next one. Again, that's a 4, 6, 5 up here. That's going to get canceled. And the next one's 5, 5, 5, so we don't need to count any. We're good. 6 and 9. Well, this is presenting a unique scenario because that's already 15. That means I can actually use a 0 here now. So we've got 6, 9, 0. And then we've got the next one as 6, 8, 1. But we already have a 186 up there, so we're good. 6, 7, 2. We already have a 276. 6, 6, 3 is a double count, so we don't need to worry about that. Starting with a 7, we've got 7, 8, 0, so that's 15. And then we've got 7, 7, 1. That's a double, so we can already stop. And then we've got the 8s and we've got the 9s. And you can count, you can add a few more in here, and you'll actually see that all of them are double counted already. It'll be permutations of what we already have. So let's take a look at our count right now. We've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 up there, and then we've got 2 down here, 9 and 10. And what we should notice is that their calculations are going to be similar, but a little bit different with the 2 at the bottom. In these 8 here, we can organize those numbers however we want. But in the 2 that are down here, we actually can't start with a 0, because then it would cease to be a 3-digit positive integer. So we have a couple of unique calculations here. The ones up top are easy to do. We have to organize the 3 numbers. So let's say we're organizing the numbers 1, 9, and 5. Well, I would have 3 choices in the first character, and then 2 remaining numbers to pick from in the second character, and then 1 last number to pick from in the last character. And what we see here is that this is 3 factorial. 3 times 2 times 1. And because there are 8 sets of numbers here, we're going to multiply this one by 8. And 3 factorial is 6 times 8. That'll give us 48 combinations from that first set of triplets of numbers. And then at the bottom here, we've got 690 and 780, but keeping in mind that we can't actually start with a 0. So what does that look like? Well, that means I only have 2 choices for my first character. Right? If I'm working with a 690, I can only choose to start with a 6 or a 9, which is why there's a 2 there. And then of the 2 remaining characters for the second slot, and then 1 last number to choose from for the third slot. This is going to give us 4. And because there are 2 sets of triplets, 690 and 780, I can multiply this one by 2, and that'll give us 8 additional possibilities. So for the no repeat section, which is all this stuff in blue, that falls into this category, and this is going to be 56 possibilities. Altogether then, we've got 1 and 12 and 56. That is going to sum up to 69, and we had 900 total possibilities to start with. So when we reduce this by 3, we'll get 23 out of 300, and that would be the probability of finding these cards that have the digits that add up to 15. That wraps up this week's problems. Check out the problems I've posted for next week's video. Try them on your own first and see how you'd approach them. And as always, if you found this helpful, don't forget to give this video a like and subscribe so you don't miss the next one.
That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.